All right. Happy 2 days after the Nobel Prize announcements. That's how we're going to designate time from now on. I'm so excited about it. Okay, so this in this problem, which is exercise 4.59, what we have here is we have astronauts are using a centrifuge to simulate the acceleration of a rocket launch. And if you don't know what a centrifuge is, if you look at it from the top, it kind of looks like a spinning cylinder from the top. Okay, and so we usually put somebody, a person, is kind of sitting out here somewhere and spinning. And what happens is if we look at a force diagram, at least from the top, if this is the person at that point, then there's some sort of a normal force acts like this. There's probably friction happening as well, friction keeping it moving along the wall, called Fs for static friction. Okay, that's that. Okay, but the normal force is what causes the centripetal acceleration. But in this problem, we don't care about that. What we're interested in is the tangential acceleration, given some things. Okay. So what we're interested in is in part A, the average tangential acceleration. Okay, and so the tangential acceleration is going to be the change in the speed. Over the time interval. All right. And so we're told that at the top speed, we have one rotation every 1.3 seconds. All right. So one rotation every 1.3 seconds. Well, first let's calculate omega. Okay. So omega is going to be how the angle is changing with time, and one rotation is 2 pi radians. All right. So what we have here is we have omega is 2 pi over 1.3 seconds, which gives us an angular frequency of 2 times pi, or 2 times 3.14 divided by 1.3, and we get 4.81 over seconds, radians per second. All right, that's the top speed. Okay, so this is the top angular speed. Okay, so that's helpful, but that's not tangential speed. Or to get the tangential speed, we need to take omega and multiply it by the radius. Okay. And so we're told that the radius that the astronaut is strapped into a seat 6.0 meters from the center. Okay, which means that if we want to calculate the average tangential acceleration, it's going to be the final speed minus the initial speed divided by the time it takes to get up to that speed. So the initial speed is 0. Okay, so we have omega final times r divided by, well, our time to get up to the top speed is actually 30 seconds. And so we get omega, which is 4.8 over seconds, times r, which is 8.0 meters, divided by 30 seconds. All right, and if you want to plug that in, we get an acceleration tangential average. That's 0.96 meters per second squared. All right, good. Okay, so that's part A. All right, and what we're asked about in part B is how many g's of acceleration does the astronaut experience when the device is rotating at the top speed? Okay, and so what we're told is that 1 g is 9.8 meters per second squared. All right. And so while this is the tangential acceleration, it's not the radial acceleration. So once we reach top speed, then my radial acceleration is going to be v squared over r. Okay. Or I can write this as omega r squared divided by r, or omega squared r, if you like. We can write it however we want. Okay. And so the centripetal or the radial acceleration is going to be, well, I'm just going to plug some stuff in here. I know that omega is 4.8 1 over seconds squared times 6.0 meters. All right, and note the units are going to work out. So I get 4.8 times 6, which is 28.8. And if I divide that, so this is meters per second squared. Okay. And if I know that 1g is equal to 9.8 meters per second squared, if I take the number 28.8 and divide it by 9.8, I get the radial acceleration is 2.94 g's, or just about 3 times the acceleration due to gravity.